Hello, chemists. This is Ms. Placino, and you're watching lesson 10.3 on determining concentration. Today we're going to talk about how to express the concentration of a solution. Turns out there's a lot of different ways to do that. Goals for today's lesson is to express the concentration of a solution in a variety of different units. We'll talk about what units you need once we get going. And you should be able, in theory, to prepare solutions of specified concentrations. We'll be spending a little bit more time on that when we are in the lab. But for now, that first goal is really the big one. We should get comfortable with these calculations. That being said, you're going to want to have a calculator handy for today's lesson, and you might want your reference table. Table T could prove to be pretty helpful. Let's get started. So we're really going to be focusing on determining concentration. And concentration isn't a really specific term. It's really just talking about the measure of some quantity of solute dissolved in the solution or in the solvent. There are a bunch of different ways to express concentration, but they all generally come down to the same format. Concentration is going to be equal to the amount of solute divided by the amount of solution. We're just going to be playing around with units. Will we use a mass unit, a volume unit? Will we use mole for solute? Kind of the same questions for solution. So I know I say it a lot, but concentration and all these calculations, you've got to be very, very careful with units. All right, so we're going to go through about half a dozen or so different means of expressing the concentration of a solution. We'll talk about what scenarios we tend to use the different units or the different expressions in. All right, so our first one is percent concentration by mass. As the name suggests, we're going to be using mass units. Technically, it doesn't matter what mass unit you use as long as you're being consistent. Often in chemistry, we'll use grams, but you could do pounds if you wanted to. Just don't mix and match units. Don't put grams in the numerator, for example, and kilograms in the denominator. That's not going to work out. Our formula is pretty straightforward. We'll take the mass of the solute divided by the mass of the solution and multiply that by 100. The mass of the solution is calculated the way you would expect it to be. I can take the mass of my solute and the mass of my solvent and just combine them. Make sure you are being consistent with units. And again, in chemistry, we tend just to use grams. We'll use percent concentration by mass when we're talking about consumer products. Trying to talk to a non-chemist about the molarity of sugar in a solution isn't going to be too helpful, but telling somebody it's 10% by mass of sugar, that makes more sense to people. Let's try out this calculation. A student dissolves 25 grams of glucose in 475 grams of water. What is the concentration by mass of the glucose solution? Go ahead and give it a shot. Unpause it when you're ready to check your work. Hopefully you've set up your problem like this. I know the mass of the solute, in this case glucose, is 25.0 grams, and I know that I can calculate the mass of my solution by adding 25 to 475 to get 500. Hopefully the math here is pretty easy. 25 divided by 500 multiplied by 100. Technically 3 sig figs gives me 5% glucose by mass of this solution. We can also calculate percent concentration by volume. You might imagine that all we do is talk about volume units instead of mass units, and we keep the formula effectively the same. And if that's your thought process, you are absolutely right. To find the percent volume, we'll take the volume of the solute divided by the volume of the solution and multiply by 100. We'll see percent concentrations by volume a lot, again, on consumer products. Something like rubbing alcohol. If you have that like in a first aid kit, they're going to tell you the percent by volume. Again, molarity and other more technical units don't make sense to the average consumer. One thing to be careful about with volumes is that they are not additive. You might think, I can just take the volume of my solute, add it to the volume of my solvent, and that's the volume of the solution. It doesn't work that way. 1 plus 1 when you're adding volumes does not always equal 2. It has to do with the way the solute and solvent will interact with one another in that solution. And sometimes you can actually see like a contraction of volume. If I were to take 50 milliliters of alcohol and 50 milliliters of water, you would expect 100 milliliters of solution. But in reality, I'm going to see less than that. I'll see somewhere in the mid 90s, depending on like temperature conditions. So I have to give you the volume of the solution. You cannot calculate it. It's something you'd have to measure in the lab. Let's try one out. A solution is prepared by dissolving 90 milliliters of hydrogen peroxide and enough water to make 3,000 milliliters of solution. What is the concentration by volume of this solution? Pause the video, try it out. This should be a pretty straightforward plug and chug. I've got the volume of my solute, just the one that's present in a lower quantity, in this case the 90 mils of H2O2. I've got 3,000 milliliters of solution, divide and multiply by 100. Technically there's just one sig fig in each of those. And you should end up with a 3% solution. If you have a container of hydrogen peroxide at home, it is most likely going to be 3%. Right. Up next, we've got parts per million, or ppm. This formula is on your reference table. To calculate parts per million, we're going to take the mass of the solute and divide by the mass of the solution. Again, be very careful with your units. And then we multiply by 1 million. So this looks very similar to the percent concentration by mass formula, except instead of multiplying by 100, we're multiplying by 1 million. A lot of times we'll use parts per million if we're talking about environmental contaminants. Telling people there's 0.000050% of lead in their drinking water might not register, but giving them a number that's a little bit easier to work with, like 50 parts per million, can make more sense. So we use parts per million often when we're talking about contaminants. A certain gas has a concentration of 2 milligrams per 100 grams of water. What is the concentration in parts per million? Be careful with your units. Pause this, try it out, and check your work when you are done. Before you can just start plugging and chugging numbers, you've got to make sure you're working in the same unit. I've got my gas in terms of milligrams, and I've got my mass for the water in terms of grams. I need to convert to the same unit. I chose to convert milligrams to grams, but if you chose to convert the 100 grams of water into milligrams, you should arrive at exactly the same place. Just be consistent. So 2 milligrams is equal to 0.0020 grams. I'm going to divide by the mass of the solution. If you added in the 0.002 to the 100, not the end of the world. Technically, it can't with sig figs, but it's going to have a pretty minimal impact on your answer. Take the value you get from this division, multiply it by 10 to the 6th, and you should calculate 20 parts per million. There's also something out there called parts per billion. What do you think might be different with that formula? Yeah, instead of multiplying by 10 to the 6th for million, we'd multiply by 10 to the 9th for billion. Be careful about how you enter that into your calculator. If you find that like you calculated either 2 or 200 parts per million for this last question, it's about how you are using your calculator, not the setup itself. Put a star next to number 4, molarity. Molarity is the preferred unit of concentration in chemistry. We'll be using it very extensively in the lab. Molarity, which is abbreviated with a capital M, is mole solute per liter of solution. This formula is also on the reference table. Let's try a real straightforward application of this. And as we get to the practice problems, we'll talk about how to make this more kind of, I don't want to say complicated, but more real world. You have dissolved 0.83 moles of calcium chloride in enough water to make 350 milliliters of solution. What is the molarity of the solution? Try it out. Check when you're done. All right, so you're given the number of moles, 0.83 moles of calcium chloride. That can go up in the numerator. We are dissolving it in enough water to make 350 milliliters of solution. Make sure that you've made the unit conversion. It needs to be in terms of liter. So I can take that, divide by 1,000 to get 0.3500 liters of solution. Then it should just be that division. Technically, I can have 2 sig figs in my answer. Now, I would calculate, excuse me, 2.4 molar. And that's how it's said, not 2.4 molarity, but I would say 2.4 molar, just like the big teeth in the back of your mouth. And the last one we're going to talk about today is molality. Yes, I know it looks and sounds very, very similar to what we just discussed with molarity, but they are 2 different units, and it is important not to confuse the 2. Molality, lowercase m, is equal to moles solute divided by kilograms of solvent. We're going to really only use molality when we're talking about colligative properties, which we will get into more detail in lesson 10.5. But for the time being, just work on kind of catching the subtle differences between this and the molarity formula. Namely, we use lowercase m, and instead of talking about liters of solution, we've got kilograms of solvent. A solution is prepared by dissolving 1.55 moles of sucrose in 2 kilograms of water. What is the molality? Pause it, try it out, check your work. Hopefully this is an easy one to solve. We can just kind of plug right in. 1.55 moles divided by 2.00 kilograms. You can go to 3 sig figs. And I get 0.775 molal solution. All right. So you've got formulas for parts per million and molarity on the reference table. Your percent composition by mass and percent composition by volume, percent concentration, excuse me, look really, really similar to the ppm formula, except instead of multiplying by a million, multiply by 100 and change masses and volumes. So one of the difficult things with concentration is when you're looking at a problem, trying to figure out which formula to apply. I really want to focus in on the molarity formula, so let's get into the practice problems. All right, I'm going to take a look at question number 2. This is a pretty real-world question for molarity. You're asked to find the molarity of a 450 milliliter solution that contains 200 grams of iron 2 chloride. This is about as complicated as I can make the problem. Before you can start solving anything with any numbers, what do you need to do first? Hopefully you're thinking that you've got to eventually find the molar mass of iron 2 chloride, and in order to do that, you need the formula of iron 2 chloride. So I've got iron, which is Fe, charge of +2, chlorine, Cl-, charge of -1, so I'd have FeCl2. Now I can work on calculating its molar mass. So I've got 2 chlorines at about 35.5, so that's 71, plus iron is about 55.8. So I'm getting a molar mass of roughly 126.8 grams per mole. When I go to solve molarity problems, I tend not to use the formula. I use dimensional analysis instead. That way I don't have to go through a bunch of little conversion steps to try to plug into that formula. I can kind of just set up the whole problem at once. So that's the way I'm going to show you how to solve these. If you prefer to do a bunch of little conversions and plug into the formula, that's completely okay as well. I'm trying to find molarity, and I know that molarity is moles per liter of solution. So I'm going to try to manipulate my units so that I end up with moles in the numerator and liters in the denominator. I know that I'm starting with 200 grams of iron 2 chloride. I know I have to get to mole, so I can use the molar mass to do that. One mole of iron 2 chloride has a mass of about 126.8 grams. Grams will cancel out, and I've got moles in the numerator, which is where I need it. I have 450 milliliters of solution. Milliliters doesn't show up anywhere in my molarity units, moles per liter, but I do see that volume is in the denominator, so I'm going to go ahead and put this 450 milliliters in the denominator and my next conversion factor. So I'll put 1 over 450.0 milliliters. I can convert out of milliliters into liters. I know that there are 1,000 milliliters in a liter. So my grams have canceled out, my milliliters have canceled out, and I'm left with moles divided by liters, moles per liter, which is the unit for molarity. Let's go ahead and perform this calculation. So basically I've got 200 times 1,000 in the numerator, divided by 126.8, divided by 450, and that should give me my molarity. I'm not going to be too tough on you with sig figs, but you should be able to be reasonable. I've got 4 sig figs in the 2 measured values, so I have 4 sig figs in my answer. The 126.8, that's a calculated value, so I don't have to worry about sig figs. 1,000 milliliters per liter, that's a conversion factor, no sig figs to worry about. So I'm coming up with 3.505 capital M for molar. It doesn't want to write it. Again, this is how I would choose to solve a problem like this. You are welcome to make smaller conversions to try to plug into the formula. If you were looking at this problem and you're like, well, wait a second, can't I just do that in one step and convert to milliliters, convert out of milliliters into liters in my head? Sure, of course you can. Just make sure you're showing your work. Try out question number 3. We'll review it together and we'll call it a day. So pause the video, give it a shot. All right, let's walk through question number 3. So ultimately, we're being asked to find how many liters of this solution can be made. So I want to make sure that I've got my final answer in the units of liters. Okay, I've gone through, I've got my formula for lithium bromide, and I've calculated its molar mass. If you rounded this to 87 grams per mole, that's totally fine, plenty close enough. All right, so I've got 100 grams of lithium bromide. So let's start getting to work on that. All right, so 100 grams, where I'll start. I don't know why my pen is being so stubborn today. I apologize. And I can convert this out of grams into moles. I know if I've got 86.8 grams of lithium bromide, I have a mole of lithium bromide. I'm going to use molarity in my next conversion. I know that my solution is 4.0 molar. So that's 4.0 moles per liter. And I would recommend using molarity as moles over liter instead of as capital M. That's going to allow you to cancel out units much more easily. So I'm going to turn this into liter over 4.0 mole. That way I can cancel out moles and I'm left with an answer in liters. Liters, and that's exactly what the question is asking for. So let's go ahead and do that calculation. I've got 100 divided by 86.8 divided by 4. Technically I can have 2 sig figs in this answer. So I think you can make about 0.29 liters of solution if you start with 100 grams of lithium bromide. All right. For these other problems, I really recommend you taking some time to work on them and figure them out. You've got a couple other molarity questions to contend with, some molality problems, some parts per million. Make sure that you're using the correct formulas. And if it's molarity or molality, I highly recommend using dimensional analysis. It's going to take a little bit of practice, so don't be frustrated if you are struggling with it a little. You'll get in enough repetitions where this stuff will start to become second nature. All right, really good job with this today, chemists. Keep on practicing. I hope you found this helpful, and thanks for tuning in.